necessarily. There we go. Okay. We are starting with my favorite section of Trig, which is proving identities. Right, that left hand side, right hand side thing. Oh no. The chapter starts with Trig equations, but I thought that would be too heavy for today. We'll just do identities. And guys, we're not actually going to be doing anything new today. We are revising grade 11.1. Okay. The only thing, thank you, that's new in grade 12 in terms of these types of questions is that we're actually going to be doing some new identities. All right, so we're going to be doing double angle identities, the compound angle identities, but the method is going to stay the same. So I think let's practice the method, get back into it, and then on Monday we can introduce the new identities. Okay, so just remember the identities that we've worked with before. Sine squared x plus cos squared x is equal to 1. Right, remember that one? So guys, you could apply it in both directions. Obviously, if you see a sine squared x plus cos squared x, that's 1. But sometimes if there's a 1, it's actually helpful to change that the 1 to a sine squared x plus cos squared x. All right, now from this, we have two other identities, or not really identities, they're results of this identity. So if you have your sine squared x, you want to make that one the subject, you're going to say 1 minus cos squared x. Again, you can use that both ways. If you see a sine squared x, it might be helpful to change it to 1 minus cos squared. If you see a 1 minus cos squared, you might be able to change, it might be helpful to change it to a sine squared. Guys, these don't work if they're not squared, right? So you can't say sine x is 1 minus cos x. That's not true. All right, they have to be squares. Okay. Then the other one from this was just cos squared x is equal to 1 minus sine squared x, like that. Okay, and then the other identity that we know is that tan of any angle is sine of that same angle or the cos of that angle. And then if you want to swap it around, you can take the reciprocal as well. 1 over tan x. Right, 1 over tan is the reciprocal of this tan over 1. So we're going to do the same on the other side. 1 over tan x will be equal to cos x over sine x. Right, so that is useful. Instead of changing this tan x at the bottom to sine over cos and then having to do a different times thing, you can actually just replace a 1 over tan with cos over sine straight away. But this identity works with squared as well. So, for example, if you have tan squared x, you can change that to sine squared x over cos squared x. The other one as well. Yes. Cos x is equal to sine x over tan x. Yes, so you can change it around like that. And guys, remember quite often that if you see a tan, normally if you change it to sine over cos, you'll get a mark straight away, unless there's like another tan at the bottom you can cancel out or something like that. Okay, but usually that's like a 1 mark almost guaranteed. Okay. Some notes. Sorry, I was just looking at what they have here. Some notes on when you're proving identities. Things that you need to look out for is look out for factorizing. Right, so often you have to just take out a common factor. But sometimes you actually have a difference of squares, a difference of 2 squares. Now, guys, this actually is quite common because if you are looking at these two identities here at the top, 1 minus cos squared x is actually a difference of 2 squares, right? And 1 minus sine squared x is also a difference of 2 squares. So often when you replace one of these, when you have a 1 minus cos squared or 1 minus sine squared, you actually then have to factorize that as a difference of 2 squares. All right, so I'm going to just write those down as examples on the side. So if you have 1 minus cos squared x, you are actually able to factorize that to 1 plus cos x, and then 1 minus cos x. Right, that's something that comes up quite often. And in the same way, if you have 1 minus sine squared x, that again is a difference of 2 squares. Remember, a difference of 2 squares, 2 terms, obviously. There's a minus in between there. That's where the word difference comes from. And both of them have square roots. Then you're going to end up with 2 brackets. In those brackets, you take the square root of each. So the square root of 1 is 1, right? And the square root of sine squared is sine. And then that is what goes in both brackets, and the plus in the one and the minus in the other. Okay, so that's something that's quite common. All right, that difference of 2 squares here. And then, of course, we need to look out for trinomials. Find an example here. So guys, something like if you have 1 plus 2 sine x plus x. Obviously, it depends on the whole thing that you're working with, but often if you see something like this, if you see a term that has a sine and a cos, right? The sine and a cos. Now, if we have like a cos x plus 2 sine x cos x, we could take out cos x as a common factor. But if there's just a 1 there, and you notice that you have a term with a sine and a cos, you're going to have to change that 1 to sine squared x plus cos squared x. Okay? So 1 is the same as sine squared x plus cos squared x plus 2 sine x cos x. And maybe you just want to take a highlighter or something. That 1 is equal to the sine squared x plus cos squared x. Now, guys, if we put that cos squared x at the back, right? So if we just change the order slightly, so if we say that this is sine squared x plus 2 sine x cos x, so this pen is hanging on for dear life. Sorry, I don't have another one now. Plus cos squared x. I'll switch over to the purple one just now, I think. But as you notice that that is actually a trinomial. A difficult one, all right, but it is a trinomial. This is similar to when you have x squared plus 2xy plus y squared. Right, that's a trinomial. A difficult one is, but the fact that you have an xy in your middle term means that you have to have an x squared and a y squared. All right, so if you have an x squared, an xy, and a y squared, that is a trinomial there. Now, when we are factorizing trinomials, because now you can't just use the quadratic formula, right? Because we're not solving for x here. This is not an equation, so we can't actually use the quadratic formula. We are going to look at the coefficient of the last term, which is 1. So this is normally the constant term, right? The last term is normally the constant. In this case, we don't have a constant term. So we look at the coefficient of the last term, which is 1. we say that we are looking for factors of 1. Right? And that's positive 1. So the sum of those factors must equal the coefficient of the middle term. So the term that has both of those variables attached to it. So 2 in this case. All right, so because that is a plus, we're looking for the sum of those factors to equal the number in front of the middle term, the coefficient of the middle term, which is 2. How about factors of 1? I mean, we only have one option. Hey, 1 times 1 will give you 1. And when you add 1 and 1 together, what do you get? 2. So the factors that we're working with here are 1 and 1. So you're going to say x plus 1y, and then again x plus 1y. Obviously, you won't write those ones. I'm just trying to show you that that's where those numbers are going to go. Right, x plus y times x plus y. And then how you would factorize that. Okay, if you want to, you can write it as x plus y squared. Okay, but if you want to get an extra multiplier, it's fine to leave it as x plus y. Now guys, what I want you to notice is that this trinomial is the same as this one. But instead of an x, we have sine x. And instead of a y, we have cos x. Right? So you see sine squared x, and we have a sine x cos x and a cos squared x. So we're taking working with 2 different variables, sine and cos. So how am I going to factorize this? If we're looking at this answer here. Sine x plus cos x, right? Wait, or just has 2 separate brackets. Sine x plus cos x. Sorry. Wait, I'm writing it as square because it's not going to allow me to write 2 separate brackets. I just make sure, sorry, if you can't read that, it's sine x plus cos x, cos brackets squared. Or you can do the 2 separate brackets. Okay. Now I'm going to have to carry on in the purple pen, how irritating. Okay. So that is just looking at the factorizing, and I've just given you guys a couple of examples that come up quite often. All right, so maybe if you are noticing something like this, in an example that you're getting, you can look at this. It's like a summary kind of things to look out for. Right, when you are working with fractions, and that's quite a common thing in identities as well, that you need to work with fractions. If you are adding and subtracting, you need to write all fractions with the same denominator, and we call that the LCD, right? So you need to find the LCD and make sure that you write all of your fractions over the LCD. And then you can put it together as one fraction. Okay, so giving you separate fractions, if you want to add or subtract, write them over the same denominator, and then write as one fraction. It's giving you a compound fraction. Does anyone remember what that means? With fractions within a fraction, or even with one fraction within a fraction. So compound fractions. Sort that out. To simplify that, you are going to times the top and bottom by the LCD of the inner fractions. And then the last thing, I'm just taking something like that here. Sometimes you have a fraction where you actually can't do anything. You guys remember questions like that. I'll do an example now. So, how can I phrase this now? Maybe I should just do an example. So say you get something like 1 plus sine x over 1 minus sine x. Okay, something like that. As a sound, please. And there's no other fraction, so you can't find the LCD. So it's not part fraction. You can't multiply the top and the bottom by the LCD. There's actually nothing that we can do. Okay, we can't cancel out the sine x's because it's 2 terms and 2 terms. We can't factorize anything here. There's no common factor. There's no difference in 2 squares. Can anyone remember what we did in this case? It was like a trick that we did. Okay. Yes, we multiply the top and the bottom by the actual name of it. I'm not sure if I even told you guys this. Is the conjugate. Yes. So of the denominator, right? So you take the 2 terms in the denominator, and maybe sometimes there's just 1 term in the denominator, then you can multiply by that same thing. For example, okay, I'll show you now. But here we have 2 terms, so we're going to multiply the top and the bottom by the conjugate of the denominator. So we're going to multiply the top and the bottom by 1 plus sine x. Okay, so we're going to put brackets around that. We're going to times this by 1 plus sine x. And we're going to times the bottom also by the same thing. The reason why we are allowed to do that is when we are multiplying by something over itself, that's the same as multiplying by 1. Remember, which doesn't change the value of the fraction. We're just multiplying by 1 in a clever way, so that will give us something more to do. Do you see that? So you could do 1 minus sine x, but usually the equations are set up in the way that if you multiply by the conjugate, it will get you to what you're supposed to go to quite quickly. But yes, it would also work if you multiply by the same. It would give you something to do. The conjugate of the denominator. All right. Yes. So that what's going to happen here now at the bottom? 1 minus sine x, 1 plus sine x. If I multiply that out, I'll do this quickly. I'm just going to do the shortcut here. Sine x plus sine squared x. Yes. Okay, and here at the bottom, when you multiply this out, you're actually going to get 1 minus sine squared x. All right, which obviously it would depend on what the other side is. Okay, you would then go on and you could maybe factorize this. This is, well, actually, that was the factorized bit, right? But you could write the factorized, or you could change this to cos squared x, right? You could just do some stuff there, depending on what you are trying to prove. All right, so this is more workable than what we have here. Okay, so what did we do here? We times top and bottom by the conjugate of the denominator. If there was just a sin x at the bottom and you couldn't do anything with whatever's at the top, then you could multiply the top and the bottom by sin x. Right? So if you change that into sin squared x, which you can then change to 1 minus cos squared. Okay, so that's that kind of trick situation where you multiply the top and the bottom by the same thing to give you more stuff to do going forward. Okay, I'm just going to give you guys some to practice. So you basically have a summary now of all the kinds of things to look out for. Okay, A, C, F, I, and L. Exercise 5.3, page 134. Under 1, A, C, F, I, and L. I can put them on the board for you. All right, guys, that is what you're doing for the rest of this lesson. You have, what, like 38 minutes, 39 minutes? All right, so you can possibly finish these. These are all already 11 level stuff, so it's just testing what we summarize now. Okay, so if you get stuck, look at the list of stuff that we wrote down and see if that helps. So if it helps. Okay, 1, 3, 4. Okay. Just number 1 and the ones that are circled, yes. Only those. Can we get going, please, guys? Okay.